next speaker is Bonington from UC University. So he's also an expert in mass generality. So I think it's good that he will also give good talks. And so his first talk, he changed the title a bit, right? So the first talk will be boundary set formalism and the null quasi-spherical formalism. So let's go to Bonnie.
Thank you for the introduction. And so my goal today is to look at these two different formalisms. Both are meant to solve this model, solving the Einstein equations in terms of the characteristic initial data along a null hypersurface, which is sort of the direction where the gravitational wave travels. So these are sort of important ways to construct solutions of the Einstein equation. And we saw some of the boundary stacks formalism in Mutao's talk this morning. We'll look at a few more details, and also we will put the Robinson-Trautmann metric that already introduced in Mutao's talk into this framework and go over the sort of the method with that particular example in mind. Okay? And then we will talk about the NQS formalism. And again, the two approach use slightly different, different gauge, but the idea is the same. You want to look at the characteristic initial data, and eventually you want to turn the Einstein equation, which is a system of partial differential equations, into sort of not really scalar ODEs, but at least you can solve them one by one as if you were solving a sort of scalar ordinary differential equations. Okay? So we'll see that the structure of both formalisms shortly. Okay? And although there's some difference in the choice of the gauge, after all, we are solving geometric equations. So if we look past through the gauge and look at some of the geometric quantities, we'll see that in fact they are fairly similar. Well, I'm not saying that there's a coordinate transformation to bring one to another. That's a separate, very interesting question. But at least through some geometric interpretation of the data, we can see the sort of similarities of the two things a little bit more. Okay. Okay. Let me just spend maybe a couple minutes on characteristic initial data for wave equations. Although we have seen the boundary stacks formalism, let's talk about this quickly. All right, so for wave equation, there are typically two types of initial data we can formulate: Cauchy initial data and characteristic initial data. Right, if we take the simplest scalar wave equation, in 1+1 dimension, right? The Cauchy initial data is probably the things that we learned in, I think, even undergrad PDE classes. Right? We want to solve this equation given the value of f and its first derivative at some level set of t. Right? So we are solving this, and then where f is obviously a function of x and t, right? And we are prescribing this. Okay, so this is a well-posed partial differential equation that we study in undergrad PDE class, and there are a bunch of ways to construct the solutions. Right, the characteristic initial data, instead of the functions and the derivative on here, for example, t equals to 0, according to my formalism. But instead of assigning f and its derivative in t on a space-like, if you want to assign the 1-1 metric to it, this is a space-like hypersurface. But instead, we can prescribe the functions on null hypersurface. In this case, null hypersurface or null lines are lines. It goes in either slope 1 or minus 1. And the simple way is to assign them here and here. Right, this is x equals to t, x equals to minus t. Right, so okay, so here I'm describing the characteristic initial data. Okay, and notice the difference here. You are presenting f and ft. Here both are functions without derivative. In a way, that's why characteristic data sets are easier to handle. If you want to study the corresponding questions in GR, then there's a whole bunch of constraint equations that you have to solve, partial differential equations that you have to solve. But in this, well, not exactly because of this reason, but at least you can imagine that assigning initial data is easier in this sort of sense. And also, writing down solutions for this is also much easier. You just write f as two functions which are x plus, two functions of single variable, and then one f g of x plus t, h of x minus t, sorry, or the other way around, I think. Then that's your solution. Right? So also getting solutions out of the initial data in this case is much easier than this one. Right? And this is the one that we already looked at in boundary socks, which is generalized to GR. We'll look at it more carefully and also sort of formulate NQS, which is also similar to this type of situation. Okay. Although in 1.1 the picture is a little bit misleading. I mean, in higher dimensions, we should really think like cones rather than lines. In this case, this is not one null hypersurface. You really assign on one outgoing cones and one incoming cones, which you cannot quite distinguish that in the 1.1 picture, although it's much easier to draw. But just sometimes there's a confusion in that kind of sense. Okay, so really, I draw both in when you generalize to higher dimension, you should really think the red part as the incoming light cone from a surface, and the yellow part as an outgoing cone from a surface. Okay. So let me write down the boundary. Coordinate. Okay. So minus e to the this is the matrix in the boundary Sachs coordinate that we see this morning, and the determinant of AB, right, independent of U and R. And if you think about this sort of level set of x2 going to infinity, then I can also say that this is the same as the determinant of the standard metric on x2. In this coordinate system. Okay, so these are the coordinate. Again, there's 1, 2, 3, 4, and then 2 more, so 5, 6 freedoms of left in this coordinate choice. Okay. An exercise that we will show the result first is we can change the Robinson-Troutman metric that we see this morning into this coordinate form. Right. This morning, of course, there the main problem is that there are this this common factor. So in this coordinate system, it's not of this form because of this last condition is not satisfied.
That's what.
Okay. And an obvious way to resolve this is, well, I want R squared times standard metric for the volume form. So why not just set this to R squared? And indeed, this is the coordinate transformation that you need to do to change this into that coordinate form. You just sub dr equals to e to the 2 lambda dr plus e to the lambda d lambda, where lambda depends on d lambda will have component du and dxa. Right into that form, you arrive exactly at a coordinate of that form. Okay? And indeed, let me just write down the result. So that form, then I'm arriving at the metric, which is, sorry, form to 2 beta is, usually this is just written capital U, but to put this into the framework that I will talk about later on, we'll set this to a function f. And V will be R, and UA will be AF over R. Okay? And there is a right. This is, I guess this part is the equivalent to the equation for phi that we saw this morning after coordinate transformation. And then there's a equations which is equivalent to the copy flow, which is roughly of this form. I will write down this more carefully later on, but at the point. So roughly du of this equals to a double Laplacian of f. Okay? Capital. This is a function depending on what my coordinate is u and.
You actually know how to write it in terms of lambda, right?
Right, but I'm writing everything in terms of this function, so. It is e to the lambda. Huh? It is e to the. Cross term is e to the lambda, I think, or e to the minus lambda.
You have some d lambda du.
Right.
Oh, dr is just
right. Right, dr is just this part. So e to the lambda is the function f.
So lambda, so that's just two. So 2 beta is equal to lambda.
Right. Okay, so let's keep this in mind. Okay, and the boundary Sachs formalism, as we recall from this morning, it has 3 sets of equations. And there's this C theta, which is HAB. Right, so this can be chosen freely on a level set of U. U equals to constant, or you can think U equals to 0 if you prefer. Or there's a hypersurface equation. All right, they determine the other metric components on the Senau cone. Up to constant of integration. These are both written down. We'll write down this shortly as radial ODEs. So you integrate in R. There's a constant of integration in R. So other than that, all the metric components are determined on a null cone. Right, there's a evolution equation which determine your free data, again up to constant of integration, which are essentially the New's function that we see, which results in the mass loss. Again, this New's function is just some constant of integration. It almost determines this data. Okay, and you can imagine at least sort of numeric. HAB is chosen freely on a null hypersurface. These tell you how to determine the other ones, and then these in turn through evolution can tell you how this change, and then this tell you derivative of this, and you can go on up to constant of integrations. Okay. And the constant of integration are determined by supplementary equation. Integration through the supplementary equation. Okay. Now let's look at them. Hypersurface equation. Right, the first one determine beta in terms of HAB, and we should keep in mind that in Robinson-Traubman, write this down first. Robinson-Traubman, HAB is just the standard metric. Okay. This particular component of the Einstein tensor, it says the following. Okay. So dr of beta is in terms of h of the metric and its derivative in R. Okay? And again, we are thinking about solving in this picture, and is solving this equation for R large into some sort of asymptotic flat space time. Although in principle we can solve on a finite region and try to solve this equation here. But here, that's think of this as we are solving this equation on R greater than some large number. Okay. So the right-hand side is determined by HAB, and if I assume some sort of asymptotic flatness, then if HAB approach the standard metric, then the right-hand side should be small when R is large, so I can really integrate to infinity. Okay. Of course, there's a freedom I can choose. Right? If I have a constant term in R, then it disappears in the derivative, right? So this determines R, as we said, it's sort of constant of integration. Beta is determined up to its order 1 transient R, or its limit as R goes to infinity along a fixed radial direction. Along a fixed direction, and then we go to infinity in the radial direction. Okay? And there's now these two possibilities. Well, if we think about asymptotically flat, then the most natural way is to choose it so that this goes to 1 when R goes to infinity. That means beta goes to 0 when R goes to infinity. But in fact, we can choose other things. And precisely for Robinson-Charman, we don't want this to go to 1. We want this to go to some function which depends on u and xa. Right. So based on that, if I want e to beta to be this, then we should choose some function f which depends on u and xa so that this limit is 1/2 log f. Right. And again, the standard choice that would make it more apparently asymptotic flat would choose f to be the constant function 1, then beta would be 0. But you don't have to make that choice. You can choose it to be a free constant of integration. Again, that would then show up through the equation and finally enter into the supplementary equation. Okay? And it's, for example, here, then it's very easy to see that indeed for the Robinson-Charman, the right-hand side is exactly 0. So it's just beta equals to this function entirely for the Robinson-Charman. So let me write this. So for Robinson-Charman, this means beta is 1/2 log f, or precisely beta equals e to 2 beta equals to f. Okay. Now the next equation, which determines UA in terms of h and beta, it will be this component of the metric, and this read right hand side we saw this morning. This, where the derivative are the covariant derivative with respect to the metric H. Okay? So beta is determined, HAB is norm, so essentially this is, again, the radial ODEs for the component UA determined by HAB and beta, which is both of them are known. Okay? And again, there is a constant of integration. If I have a component of this which decay at the rate r to the minus 3, one more derivative is r to the minus 4, order 1, which disappear in the derivative. So it's determined u to the a up to a constant of integration, which is of the order r to the minus 3. Okay? So UA is determined up to a term L of this form. L, later on, this will be related to angular momentum, although I don't think I will have time to go into that, but that's what why it's labeled in this way. Eventually, this will be related to angular momentum. Okay? And again, for the Robinson-Charman, this part is 0, and beta is just this function. So we would means that is exactly gradient f. I think there's another factor of e to the 2 beta you multiply to the other side to cancel it out. Okay? And well, in principle, you could still add a term of order r to the minus 3, but that is chosen to 0. So that later on, when we iterate this into the next hypersurface equation, we don't get a bunch of tail terms in the expansion for V. Okay? So this is this. Then finally we have the equations for V. Which is this. Right? This is the Gauss curvature of the induced matrix HAB, which will be Gauss curvature, scalar curvature, 2 plus lower order terms. Okay. And again, this when you integrate, there's an order 1 term for V, which you can choose freely, which is related to the mass aspect function. Okay. And if you work out the Robinson-Troutman matrix, beta is essentially log f. UA is gradient f. So there's also e to 2 beta term I have to multiply to the right-hand side to 1. And a bunch of cross terms cancels out. So at the end, what you get is for Robinson-Troutman. You get exactly R. Sorry, the two positions are normalized differently. If I write in that form, I should write R here. Plus F. And minus an order 1 term is 3, and for whatever reason it's chosen in this form, where M is a constant for the Robinson-Troutman metric. Okay. Okay. At this point, in principle, M can be a function of U and XA. Later on, with the supplementary equation, we can actually justify this choice of M being constant. Okay. Is this. So essentially, we recover most of the metric component in the Robinson-Troutman metric. So we recover all of them except this last equation. Okay? So let me erase these now. The evolution equations, it comes from the vanishing of the traceless part of EAB, E capital A capital B. And formally it will be of this form. One derivative in u times r, then take one more derivative in r, equals to, so this I will indeed not write this down, on the level set. Okay. But again, it almost determines du of HAB, except there's a term of order 1 over r, which you cannot detect. Right, so this again determines u of HAB up to a term which is minus 1. Okay. So in the standard bounded coordinate, if we write HAB equals flat metric plus this term plus this. I mean, this is the fixed flat metric, the standard metric on S2. This whole tail is determined by this equation, but we're left with the freedom du of CAB. Right, which is essentially this freedom. And this is usually referred to as the New's function. Okay. So at this point, we solve, and again, there's a trivial equation that would automatically satisfy because of the, well, I should really say evolution equation, trace this part of this thing, but its determinant is standard, is the same as a flat metric. So once the traces part is determined, the trace part is determined as well. Okay. This determines almost everything except that we have m, which depends, a scalar which depends on A, where we have very bad notation. I have a vector field on X2, which depend again on U and XA, and then I have either this or F. If I'm in Robinson-Chalmers, I have this freedom, or in the usual case, I have this. In fact, you can combine both to have both degree of freedom into your equation. That's fine as well. Okay, so we're left with this, and we'll attempt to solve the supplementary equation from this left-order degree of freedom. And the supplementary equation, again, from the Bianchi identities plus the 7 components of the Ricci curvature which already vanish, one automatically knows that R squared times e to uu and R squared times e to ua satisfy a homogeneous equation. All right, so our goal is, this means that if they vanish on this picture, if they vanish on any level set for R, then they will vanish completely on the null hypersurface, because we can integrate this in the R direction. Okay, and as mentioned in this morning, so again, level set can take R at infinity. Okay, so we do need R squared times this to vanish we can either ask E to U to vanish on a finite surface of R, or we can ask R squared times this, the limit goes to 0 when R goes to infinity. And if we're expanding everything in terms of power series in R, then the latter is easier to do than the former. So we will ask that goes to 0, and it goes to 0. And this combined with the equation will tell you that it vanished completely, at least on the null cone. Okay. Another thing to notice, which is probably not as important in this case because naturally these two things will decay at 1 over R squared as long as you write down the equation. So in fact, both of these will decay like 1 over R squared. We're asking that the leading coefficients to be 0, then it will be 0 completely. Okay. Okay, so let's say what is this equation means. Okay, well, you write down the metric and you essentially you isolate the term which is 1 over R squared, set it to 0. Okay? And one can notice is something I should have said here. Although in the two cases, the equation would look differently, one can interpret this sort of in one equations together. If I set capital N, I redefine functions to be this m over x to the power 3, okay? Then in both cases, I can write down this equation at the same time. Of course, if I set f to goes to 1, then this is just, I just renaming the mass spec function small n to be capital N. But in the case of Robinson-Trautmann with a capital F, I do need to do this change. It will be twice of du of m equals to double divergence of a tensor NAB minus norm square, where m is the 1 over R turn of the surface sigma R of the inward traces part of the inward second fundamental form. Of a level set. So I have a level set like this. Right? There's a DDR, which is a null vector pointing outward. There's a L underscore or L bar, which is perpendicular to both dr and the surface, and it's a null vector. There's a unique such null vector up to some receding. And essentially, I can look at the second fundamental form in this direction, take its traces part, it's going to decay at the order 1 over r, and NAB is that leading order term. Okay? If I'm in the usual boundary coordinate where g of ru goes to 1, and then I'm driven everything by this, then it's simply 1/2 of derivative of sigma AB. Again, my metric is, I think I erased this somewhere. This is my metric. Derivative in u essentially is the second fundamental form in the inward direction. So du of CAB is the leading order term of the traceless second, and also CAB is traceless. So this is the leading order term of the traceless part of the inward second fundamental form. And in the Robson-Trautmann case, the metric is standard, but there's a coefficient in front of du squared. So this is indeed the also the thing we see this morning. Essentially the traceless part of F, which you also see this morning in the mass loss for the Robson-Trautmann. Okay? So in fact, geometric, if you interpret everything geometrically, it's the same formula. Mass loss is double divergence of this second fundamental form minus its norm square. Okay? And the integral of the mass aspect in fixing u and integrated in the x2 give you the total mass of a null cone. Right? And this exactly tells you that the mass is always decreasing. And if you write double divergence of this and commuting a few derivatives, you will see that the leading order term is the double Laplacian. So it's not in the same form as the equation we see this morning, but this, if we plug in this second fundamental form, is equivalent to the copy flow we saw this morning. And although there's two slightly different situations, again, geometrically that remains the same. Mass loss comes from the inward second fundamental form, and exactly derivative of mass aspect is double divergence minus norm square of that traces two tensor. Okay. I also promised something. So this other equation, I will not write it down completely, but it can be roughly of this form. Derivative of the angular momentum aspect over derivative of the mass aspect equals to f. There's a term involving gradient of m plus something else. And those something else equals to 0 in Robson-Trautmann. And if you, in Robson-Trautmann, in order to have a finite extension, we set this to 0, which through the supplementary equation implies that gradient of m, which potentially you could imagine it being a function, but its gradient actually equals to 0, so you have to be a constant, at least along each null cone. Then I believe you can probably rescale your u direction to make it a constant on the whole space, I think. So through this equation, you can actually see that m has to be constant. If you persist that the angular momentum aspect equals to 0, which is the case for the Robson-Trautmann. Okay? And there, I think at this partially, if you introduce this low order terms in UA, then you get a whole bunch of low order terms in the metric, and you don't have this nice sort of very simple answers. Okay. So this is one thing, and one final remark, sort of to prepare for my talk next week. Well, we have this picture, incoming and a surface, and an incoming and outgoing null vectors. You can decompose all the geometric data in terms of this friend, right? The Weyl curvature tensor you can decompose. In this friend, you have the also second fundamental form in these two directions. Right? So you can decompose ambient curvatures and the extrinsic curvature of the surface in this friend. And we're talking about asymptotic fatness, or asymptotically fat non-infinity. So obviously, all of this quantity should decay as R goes to infinity. The most significant ones will be a component which decay the slowest. Right? So there are one component for the ambient curvature and one component for the extrinsic curvature. Extrinsic curvature that decay slower than the other, both at the rate 1 over R. The first one we already see here. The inward, the traceless part, well, I guess the mean curvature in both directions obviously decay at 1 over R. Those doesn't really count. Those happens even in Minkowski. The other thing that's R0 in the Minkowski space, the one that decays slowest is, the first one is this, the inward second fundamental form, which decay at the rate 1 over R. There's another component of the the ambient Weyl curvature tensor which decay very slowly as well, which is usually denoted by alpha bar. And this is the Weyl curvature evaluate in L bar, and then add the two tangential direction, L bar A, L bar B. Again, this is of order 1 over R. And when I say order, I do mean plug in vector of unit length. Right? Otherwise, if you plug in vector of length R, then second fundamental form in that component will be of order R. So when I say 1 over R, I mean plug in unit vector. So similarly here, we are plugging unit vectors in here. Okay, so these are the two main components. There's a component which decay at 1 over R squared, but nonetheless is very important in the discussion later on for gravitational radiation, which is the shear of the null hypersurface that, well, the Robertson-Troutman is derived so that the null cone is shear free. The shear of that null cone, although it's of order 1 over R squared, is again fairly important, and that shear is the traceless part of the second fundamental form in the direction of L. So the outward traceless second fundamental form is of subleading order, but these three putting together is still very important for the following reasons. Well, first of all, it's easy to see that this is proportional to CAB over R squared. I think there should be a factor of 2 or 1/2 somewhere. Okay, and I already tell you that the 1 over R term is derivative in U of this. And in fact, it's fairly straightforward to check through this computation and see that in fact the leading order term in alpha AB is in fact roughly du of NAB over R. Again, this factor of 2 or 1/2, and also depend on how you normalize L and L bar. But essentially, this three quantity forms a sort of second order ODE systems. This is the Lewis order term. Derivative give you this. Second derivative give you this term. So second order derivative should remind us position, velocity, and acceleration. And indeed, that's the correct interpretation because this is biocurvature. So if you look at the Jacobi field equation, which gives you geodesic deviation, and because we are in asymptotic flatness, so distance displacement is roughly to leading order geodesic deviation. So if you look at the Jacobi field equation, which is second order derivative of displacement in this case, will equals to this. So indeed this, if we're doing gravitational wave experiment, one should really treat this as the acceleration. And because it's two derivative of this, so I should really treat this as position. And I should treat this as velocity, and this as acceleration. Okay. So we'll come back to this.
You're putting too many things together.
Right, but this is just, come on, we'll do this more carefully next time. But for now, we should, right, this is the component we see in mass loss, okay? And the two related components. Next time when we treat this formally, we'll write down every component and its appropriate decay rate. But, forget about Jacobi field equation. At the moment, just remember that these three components, they satisfy a second order system. I think that should be sufficient for now. So you have the largest term in the biocurvature tensor, the largest term of the extrinsic curvature, which is the inward second fundamental form, and a subleading term, which is the outward second fundamental form, which is a shear. These three, both of them are traceless symmetric two tensors, and they satisfy a sort of second order OD system. So one is the derivative of the other. Okay. And the order is this second fundamental form, the first derivative in U or in time give you this second fundamental form. Differentiate again will give you the leading order term of the biocurvature tensor. Okay. Okay, so let's see. See how much. So for the NQS gauge, we will write down the space-time again, roughly model over a null cone, but with a different gauge choice. Okay. So since this morning, for the boundary X, there's a sort of derivation of why one can end up with this sort of gauge. Here we'll just write it down directly. Assume our space-time has such a coordinate system. So again, you have 6 degrees of freedom. And we want to make the induced metric on the level set as simple as possible. So it's just a cylinder metric. And unfortunately, the same symbol I used to mean very different things in NQS compared to boundary X. So bear with me. So we're keeping the metric as simple as possible. In front there's again u is replaced by z. It's again dz dz and a cross term dz dr. But we reduce the degree of freedom here, so we can no longer require dr is perpendicular to dxa, but we still want the null cone, so we still want the complete square here, so that if we set z equals to constant, we get a null hypersurface. So there's a complete square here. Okay. So again, if I set z equals to constant, this goes away. I get the induced metric on level set of z is this, which is still of signature 2, 0. So it's signature 2. So it's still a null hypersurface, just ddr is no longer a null vector. But on z equals to constant, it's still a null hypersurface. Right? And again, I get 6 degrees of freedom. There are 2 scalar functions and 2 vector functions here and here. Obviously, so this is the setup here. Obviously, beta was a function in the bounded set, and u was a coordinate, but and the free data that we can choose on a null cone, so null hypersurface, is this vector beta of A. Okay. And also, going back to this picture, although we have standard metric here, because XA and DR are not perpendicular, so when I compute the second form inside the null hypersurface, I still get something non-trivial. Okay, and in fact, I will get derivative of beta. So even though I have, so if I want to compare to the previous picture, I'm still prescribing the shear of the sphere in the null hypersurface, just in a different coordinate and gauge form. But I'm still prescribing this inside my null hypersurface. Okay. Yeah, sure. And the other difference compared to bounded sets is this use a formalism which is closer to Newman Penrose, meaning that you complexify everything and write a vector field as complex numbers. You write a vector field as a complex value function. Right? So identify beta A with a complex value function, beta 1 plus I beta 2. And let's use this. Well, we want to differentiate this things, and how you differentiate is, again, it's covariant derivative with respect to the standard metric on S2, but this is packed in this S operator. Okay. So even though we're treating everything as a complex value functions, I mean, when you differentiate scale functions, vector field, 2 tensors, or covariant or contravariant tensor, they should be differentiated differently. Right, so this is through the S operator with the spin weight, so that you can write down one operator which differentiate all the tensors of different.
Maybe you can explain how you treat it as a complex variable.
So if I choose a coordinate system, theta and phi, right, I have this component, and I can just identify.
This is a vector, right? I mean, beta I is a vector.
Right. Right. So beta I has in coordinate system these two components. Then that means I. Sorry, my bad. Beta is write it this way. Otherwise, I confuse myself. If I write it this way, then I will identify beta with this complex value function. So I already have, well, my matrix is the standard matrix, so I have theta phi, which is almost a global coordinate system. So if I write down beta in terms of this coordinate system, beta 1 dt theta plus beta 2, I think this is a vector of length 1.
That's also normal frame.
This is also normal frame. Right? Then I write beta as the following complex value functions in this also normal frame. And I think this is not sure about this vector, but
You use this complex basis.
right.
E1 and E2.
Right. I guess it's 1 over root 2 E1 plus IE2, and then 1 over root 2 E1 minus IE2. Right. Okay, so I can identify vector field with complex value functions. Of course, when I different, and I can identify. Well, if I have a two form, then I have the trace part and the traceless part. The trace part is a usual scalar function. The traceless part in the also normal frame can be written down in this way, which again you can identify with a complex value function, a plus ib. Okay? So I can identify, well, scalar function is just scalar. Right, vector field or traces two tensor, I can identify them with vector field. But when I differentiate the actual vector field, this function should be differentiated differently with respect to this, because this comes from a 1 form. Well, this is a vector field, this is a 2 form. They should be differentiated differently. And this is factored into the S operator for the spin weight. This is correspond to a vector field, which will have spin weight 1. A 2 tensor will have spin weight 2 or minus 2. 2. This will have spin weight 2. Okay, so depending on the spin weight, when I differentiate a complex value function of spin weight S, when I differentiate it will be the following. Okay. So if I apply S to a complex value which has spin weight 1, so if I have differential vector field, I should put x equals to 1 and do the derivative. And you can see that the corresponding crystal symbol will show up and give you the correct derivative to differentiate vector field into two tensor.
I don't understand. When you write down everything, you draw kind of thing.
Right.
In terms of the original component.
Right.
So in some sense, the second line, something quite, to me, is quite troublesome because you did not use the exact d-bar field. And then inside
This.
Then inside you spell it as d-bar. But you did not use the operator. You rewrite it in terms of original tensorial and covariant derivative.
Right.
So what's the point of introducing complex value kind of tensor or spinner, whatever? I mean, the right hand side obviously is the return, the restatement of the tensorial kind of derivative. So it's really not a differential operator of the left hand side of the notation. I don't see what the point of introducing d-bar or d-bar. To me, the complex value, everything in some sense is there. Just kind of doing it.
I think this sort of, well.
To me, tensor is tensor, it cannot be a function. Because you introduce the spin weight,
Right.
to me that's exactly the weight of the tensorial.
Mm-hmm.
So there's no point of introducing complex value kind of thing.
Because this is actually working on basically S2. So it's actually treating them as sections of holomorphic line bundles. You can actually interpret it that way. And this S operator is actually d-bar operator. So you from complex functions, you can holomorphic 1, 4, or 1, 2, 4. You keep on doing the d-bar operator. But they don't like the d-bar operator. So this is a even for projection, you take a d-bar, you still need to respect the line bundle transformation. Yeah, that's right. So the spin wave will correspond to.
Yeah, that's right. So that's why this spin wave is not the
Right.
tensorial wave.
Right.
It's nothing.
It's actually all of them are actually sections of powers of canonical line bundle dz. So dz to a certain power,
Right.
and the power corresponds to the s.
So something you introduce without notation means the complex structure of the CP1.
Yes, but right.
You can interpret everything in that.
Or you can write everything in terms of the usual covariant derivative to unpack the notation, which at least for me, I have to do that in order to actually understand this sort of thing. But I'm not really used to thinking about this in terms of holomorphic one form. But the spin weight in principle should take care of that.
But in your case, I think you're only concerned about one form. And then there's this operator, you take covariant derivative and take the traces part of it.
Right.
And then the divergence of it.
Right.
And that actually just corresponds to the complex form, the trivial line bundle, dz.
Right.
And the holomorphic, and dz is good.
Well, because it's surface, we only have one form and two form. Right. Okay. Let's see.
It's actually better to rewrite everything.
Eventually, I will do that. But so this notation make the equation seemingly very compact, but then you have to unpack everything.
It seems that for computer
You just change the spin weight along the way. You can.
physics,
Okay. This is the first difference to notation, formalism-wise difference compared to the bounded set. The other one is in bounded sets, one computes the metric coefficient directly. Erase a lot of things. Right. The hypersurface equation there, what we solve, v e to the 2 beta ua, those are metric coefficients. But for the NQS gauge, the formula is to, instead of the metric component, one would solve the connection coefficients. So let's define the relevant connection coefficients. They are four of them, which again, two scalars and two, I guess this will have spin weight, one symmetric traces, two tensor, one vector fields, and then two scalars. So connection coefficient. So this is the, if we come back to that picture, this one is the mean curvature in the direction L. And the second one, the traces part of the second fundamental form, as we said before, is S of beta. And this is correspond roughly to the mean curvature in the inward direction. Sorry. This is the traces part of the second fundamental form in L bar. And this one is the connection 1 form of the normal bundle.
What is the next last term? In Q. In Q, capital Q. What is that?
Gamma plus, this operator applies to gamma.
What is that operator?
DDR minus R minus 1 gradient beta.
Oh, that's a beta.
Beta, right. This is a beta. So this operator applies to beta minus this operator applies to gamma plus gamma.
What is that operator? What is the DDR?
DDR. This is DDZ minus R to the minus 1 gradient beta, DDR minus R to the
gradient beta applied to beta.
Right.
So, what does that mean?
Well, you have a covariant derivative of beta in its the net result is still at 1 form. Just
So now you just read it
Right.
as a vector. Beta as a vector.
vector field. Okay. So one can, from these, one can recover the metric component. Again, assuming beta is already known. For example, if you know H and beta, then you can figure out U. Knowing okay, so for the formalism, instead of the U, V, and gamma A, one would look for these coefficients first. So again, there's a set of equations which one can think of then as the hypersurface equation, which determines H, J, K, Q on a null hypersurface in terms of the free data. So if we write this operator, DDR, minus r to the minus 1 d beta, and also another problem is my r and gamma are the same. dr is partial r minus r to the minus 1 covariant derivative in beta. Then I can write down hypersurface equation which determines this on a null cone. For example, E Einstein tensor in the LL direction equals to 0 imply times h. Okay. So again, once beta is known, this operator is known, and then we can determine h from this equation. Again, up to the limit of h when r goes to infinity. Although slightly different. I mean, here you can choose that leading term, but then the lower term would depend on that leading term plus the information on beta before you have dr of a component equals to some given thing. So the older one term can be chosen freely. The rest determined by beta here. Slightly different. You have a freedom to choose this limit, but obviously the lower term would depend on what you choose. But once you choose that, then you can write down the rest. Okay.
What is the capital L here?
The outward direction.
Yeah, but what is in terms of R and Z?
Grad Z, whatever grad Z is.
Grad Z is true. It's proportional to grad Z. Well, and so being 0, so I can put grad Z in there.
It's not DDR is DDR there. It's not,
right.
DDR is not null.
DDR is not null, so it's not that direction. So it's not this whole thing. It's probably DDR minus beta A dxa, or
But it's not DR.
not dr.
It's not
It's not dr. You're plugging the null vector.
Uh-huh.
You're plugging this null vector.
Yeah, DR is the operator.
dr is this. Well, is this?
DR is DR now. This considers the vector is it now?
I don't. G R R B A B C think this is not. R is, well, actually, yes. I think you get, all of them are beta norm square. You get +1, and then -2. So I guess you are differentiating H in the null direction equals to something null. And before dr, again, in the boundary stacks, dr is the null direction. So you're differentiating this unknown in the null direction equals to something.
That's kind of, H is the mean curvature.
Which, I guess, because you can normalize null friend by multiplying u or 1 over u. I think it's proportional to the mean curvature, but up to scaling this vector by -u. Okay. And then there are I should get 6 equations because I want to determine 6 components. So this will give me a equation which determine Q in terms of things that I already know. Once I have H, I can recover U. So this will be in terms of beta U H and Q. So I'll get, again, a radial ODE for Q from this equation. And then, this should account for two equations. Determine Q completely. R equals to 0. This will determine D of J. And one component again trace this part of EAB will give me R dr of K equals to something. Okay, so again, it's going to be a system of nested ODEs. From beta, I can solve for H. From H, beta, and other things I can determine from them. I can solve for Q. I can solve for J, and then finally we solve for K. Okay. Now, however, even though this is labeled as hypersurface equation, which is what they look like, this in fact already include the evolution equations into this whole big set of nested ODEs. Evolution equation, remember, the free data on the cone is the vector field beta. So my evolution equation should tell me how to differentiate beta in the time direction, in this case, differentiate in z. Right? But if you look at this last equation for Q, there is indeed a dz of beta, and then the rest is terms derivative, which is determine tangentials to the cone. Right, so in fact, from Q, from the definition of Q, if everything is known there, then we can recover dz of beta. And again, this, if we view like beta is the free data on the cone, dz of it, what determines this should sort of is our evolution equations. Right? So indeed, Q already include the information of the evolution equation into this big set of equations.
Can you, well, I'm still quite, so free data is beta A
On a cone.
on the cone.
Right.
And then how do you determine, I mean, what about other metric coefficients, UV and gamma?
UV and gamma. For example, I can determine H from this.
So you start with beta
I can solve H
on
on a hypersurface.
Okay.
On surface, right? Then I look at this equation,
Okay, that gives
knowing
you,
that will give me U.
yeah,
Then I can solve for Q.
So now you have beta, U and H.
Right.
And you can solve for Q.
I'll perhaps let me write down this more carefully. For example, this equation would it's not really that useful. But again, you have beta U and Q, beta U and H on this side. So you can determine Q from here. And the equation for J, I think this literally depends on J, U, Q alone. Does it have?
Once you have Q, you come back and this give you a
Actually, no, we solve this completely, then we come back. Here on the right hand side, other than U, there's no other metric coefficient appearing in the right hand side.
Okay.
So here you literally go exhaust all the hypersurface equation for the connection coefficient first. Other than
You also have one for K.
K, right? Which would read RdRk equals to 1/2 divergence beta plus I curl beta k minus 1/2 J s beta plus 1/2 U s q plus 1/4 U q squared.
What is the curl of beta? Is it S beta?
Curl of beta.
How is curl of beta different from S beta?
Curl beta will be S beta minus I of S bar. Curl beta and S beta are different.
But beta is one form.
Beta is a one form. S beta is actually a two form.
Beta is symmetric
Symmetric, right.
What about curl?
Curl is a scalar. I guess it's a two form, but then you identify with a number.
Okay.
Right.
So that's D of E.
I think divergence of beta would be divergence and curl, they are related to S beta bar and S bar beta.
But divergence is actually the divergence of the one form.
But divergence one form, curl over curl.
D of the one form.
Right.
And S is the one that gives you a symmetric traces.
Right. So again, on the right hand side here, there's no metric coefficient, well, other than U. And you solve all of this first. And then from all of these, one can recover the metric coefficients.
And then on the right, so you have, you decide U from the equation of H.
Right.
And you determine divergence of gamma, while you also have
I think you can solve gamma and V out of these two equations together. I didn't write it down. Let's say from these two together, there is a S gamma equation that you can solve for gamma. Then V can be recovered algebraically. Let me. Wait, I didn't bring my computer. Do you remember the equation? I think from these two together, one can. One can read. Right, you can eliminate V from this equation. I think from these two, one can solve an equation which is S of gamma equals to things that are already determined. So I think one can eliminate, well, I guess, because V is a scalar, which you can write in terms of beta, k, and gamma, put it into this equation to write it as a differential equation for gamma, which is roughly of the form S gamma equals to something.
Equal to something related to divergence? Or?
Related to something J and K, and then gamma itself. And one solve gamma out of this equation.
But that will involve gamma and divergence of gamma.
Let's see. Let's see.
S
gamma
plus divergence of
gamma equals to.
What is
Yes, asymptotically, if we have some asymptotic determinant for beta, at least in those settings, we can solve gamma order by order, because this will have the same order as gamma, but this part will have lower order because of the beta in front. So I think at least K, J. For example, if you have a beta has some power series expansions,
this should be electron equation for gamma. I mean, this is the first order operator.
Right.
Sorry, is the N operator promoting the thing to a higher spin level? It seems like
Right.
they're not in the same spin level. Terms. J is not in the same spin level. J scalar.
But it seems that it's still a first order
It's
electron
equator for
gamma.
gamma.
Then don't you have to make sure that your right hand side is perpendicular to the kernel?
Right. Right. I think one have to. Yes, one have to make sure of that. I think this one. I think this is. I think. Well, the S beta. This is now everything is in spin 2. This is a PD. I guess one have to make sure this is solvable. I think if like beta has a decay rate, then I think this is as going from vector fields to symmetric traces to tensor
Yeah, but the kernel are exactly the first
function.
for the S operator, right?
Right.
I mean, if a trace is symmetric to
Tensor.
then you multiply by the first
Function.
That's equal to 0.
Right.
But how do you know the right hand side is perpendicular? I mean, what even in the case when beta is equal to 0.
So just S of gamma equals to KK.
When beta is equal to 0.
Right. So vector field. This has, but this map onto traces symmetric to tensor, right? The S operator. I mean, there's a kernel, but I think the map is on. The map is onto.
What is that? Oh, okay. Oh, this is on.
So the map is onto. This has a kernel, but it's onto symmetric traces to tensors. So this when beta has a power series expansion or some sort of expansion, you can solve order by order. Did in terms of gamma, in terms of did in terms of k, put it into the right hand side, solve the next order term for gamma, and so on and so forth. And then I think once gamma is solved, then V can be solved algebraically.
So for vectors, it's at length of traces symmetrized gradient or something. You say it's not.
Right. This is S bar, but I think this is. I think it mapped basically the tensors to the symmetric traces part of the derivative.
Symmetrized gradient.
Right.
But is it but beta K what is K obvious? Oh, okay. K is symmetric traces.
Right. I think everything here is in this equation. Everything is symmetric traces to tensor. Right. We apply S to a vector field other than this term.
That's also
K is symmetric traces. So it's an equation of symmetric traces to tensor. Then S is onto that. So, but again, there's a divergence, but I think one can argue if beta is small enough. When beta is small enough, this is the operator, and it's onto the symmetric traces to tensor. So gamma can be solved from this equation, and from here, V can be solved algebraically. And once everything is known, then from Q, in Q, every other term is already determined on a null cone. Then one can indeed recover dz of beta from Q. Once beta, gamma are all known on a null cone, and Q is known on a null cone, then one can recover dz of beta, which serve as the evolution of your free data. Okay. So again, what's left is the supplementary equations, which would determine the constant of integrations from these equations. Which write down this. For example, the equation that z equals to 0. Again, the Einstein equation in the z direction. So again, the same equals to 0 implies this equation. And in J, if you combine this equation, there's r d of j plus j equals to lower order term. So dd of rj equals to something. So there's a 1 over r term of j, which is free, which is the mass aspect. And that is determined in this equation, the order 1 term equals to the order 1 term of the right-hand side. And if you see the right-hand side, there are a bunch of divergence term and Laplacian term which integrate to 0. And the one that will contribute will be this. This asymptotic to 1, so twice of the norm square of the second fundamental form. So roughly this will translate to this equals to plus divergence of a big thing minus and some factor. So again, minus k norm of k squared would serve as a source for the mass loss. And again, k is the traces part of the second fundamental form. So again, even this is in different gauge and formalism, the traces part of the inward second fundamental form is larger than the other component, and it's driven the mass loss. Okay, so I will stop here today.
This is true reference because this computer are quite complex. Tony can do all the. But maybe I will post this paper on the web page